Hello, my name is Cameron. Today my teammates Kevin Liow, Amadou Diallo, and I will be presenting to you our year's work on the Haiti Solar Relay Project. We work alongside our graduate mentor Kartavya Agarwal and our faculty advisor Dr. Divan. Haiti is one of the most impoverished nations in the world, with 24.7% of the population earning less than $1 a day. Of the rural population of Haiti, only 4.3% have access to clean fuels and technologies for cooking, and only 2.75% have access to electricity. These statistics inspired the creation of the Haiti Solar Relay Team. We work towards the goal of providing cost-efficient, reliable electricity through a portable solar home system deployed in the rural-most areas of Haiti.
Our current Haiti relay runs on a 12-volt 7 amp-hour sealed lead-acid battery. It comes with a 2 USB port output, and on one full day of charge, it can provide approximately 5 hours of house lighting or approximately 2 full cell phone charges. In 2019, we've delivered 20 relays to Haitian entrepreneurs to sell. Since then, they've sold all of them and are waiting for more shipments. Since the summer of 2018, when we first started, we've sold over 50 relays. With all these relays, we've gained quite a lot of data. The data has shown that the batteries in these relays need to be replaced approximately every year due to it being used daily. This model with the sealed lead acid batteries is not sustainable. This fact has motivated our team this year to really focus on improving and prioritizing the sustainability and cost effectiveness of our Haiti relay.
So our main goal is to develop a product that is compact, portable, cost-effective, and most importantly, easy to use. And in order to bring this goal to fruition, we created the Haiti Relay. This year, in order to continue the optimization of our system, we plan to replace our sealed lead-acid batteries with our lithium-ion batteries. This is because lithium-ion has an average 5-year lifetime, which will lead to a drastic reduction in overall cost to consumers over a 5-year lifetime. As you can see to the diagram on this page, we have our Rev B, which is a sealed lead acid, connected to our solar panels.
The four major hardware components of our system design are the solar panel, charge controller circuit, the load, and battery. As stated by Amadou, the main difference in our design from previous years is that we are transitioning to a lithium-ion battery. For our system in particular, we use four 3.7-volt lithium-ion cells in series with a 15-watt solar panel and a 5-volt USB load capable of charging a phone or powering a light bulb. With our charge controller circuitry, we will maximize power path selection between the panel, battery, and load. We will also provide protection against overvoltage, undervoltage, and short-circuiting. When considering what IC would best suit our system, we have to consider cost-effectiveness along with the availability of an evaluation module and documentation to guide us.
All of our hardware components revolve around the Charge Controller Integrated Circuit, or IC. It functions as the brains of our system. As Carah mentioned, the Charge Controller IC will control the power path selection between the load, battery, and power supplies to maximize the lifetime of our lithium-ion battery, all the while protecting it from things like short circuits. An example of our charge controller working is when the battery is fully charged or undercharged, the charge controller IC will automatically disconnect the lithium-ion battery from the rest of the circuit. This decision-making is all made by the IC measuring certain parameters of the battery, like battery voltage, the load, which is the resistance of the load, ensuring that it doesn't draw too much current, and the power supply, which in our case is a solar panel, and that is based off of available sunlight. When certain thresholds are met, a microcontroller will send messages via serial communication to switch the IC to the corresponding state it needs to be in.
In order for this project to work, we need to ensure that our chosen IC, the TI-BQ24780S, meet our system's requirements. We were able to acquire an evaluation model from TI, which helped us test our system requirements. In order to do this, we connected the EVM to a computer, and using BQ Studio, which is software given to us by TI, we're able to change registers in the SM bus. Each register controls different parameters such as charge current and charge voltage. We also tested the EVM with a DC power supply and lithium-ion batteries to ensure that the IC is working properly once we implemented it. Lastly, we're going to test our EVM with our solar panel connected and have our output as a light bulb. Here you can see our experimental setup. We have the picture to the right is a close-up of our EVM, which has test points, a power supply, and our load and battery. The load in this case would be our light bulb, and our power supply would be the solar panel. Here we can connect our test points from the EVM to an interface board, which directly we can connect to a computer and use the BQ Studio software to test our system. We also have a 4-cell series lithium-ion battery.
Upon completing the experimental tests that Amadou just highlighted, we were able to come up with a few experimental results. One result was that our charge controller was able to set up a constant charge current and constant charge voltage to the lithium-ion battery. This is important because a lithium-ion battery that is not charged at constant current or constant voltage could permanently be damaged. Also, we were able to discharge and charge the lithium-ion battery within 10% of the desired thresholds. This is important because our charge controller worked by disconnecting the lithium-ion battery before it was overcharged or a state of undercharge. And when a lithium-ion battery goes beyond these thresholds, it could also permanently damage the battery. We were also able to control the power path selection depending on available power. We did this by connecting the charge controller to the DC power supply and to our lithium-ion battery, and also a load. The load would be powered on by whichever available power there was, meaning that if the DC power supply was not supplying enough power, our load would be drawing power from the lithium-ion battery. However, if the DC power supply power was increased and it could provide more power, our load would be drawing power from the DC power supply and not our lithium-ion battery. This simulated a solar panel based on available sunlight during the day. Lastly, we wanted to ensure our system would be able to work with loads that would be used in Haiti. So we were both able to charge a phone battery and power an LED bulb with our system. Similarly, we wanted to ensure that our system functioned with the power supply it would be using in Haiti, the solar panel. Unfortunately, we were unable to provide enough power to the EVM with our current solar panel. However, our charge controller design will have a lot less components than this current EVM, which will ultimately draw less power, and we will be able to test it in the future with our future design. Also, we ran a lot of tests with the DC power supply, varying how much power it could supply to our system, and our IC was able to handle it all. So we are confident that the IC and the EVM will work with a solar panel.
Based on what Kevin explained, our chosen charge controller should meet all of our hardware requirements, but software is also needed to control the integrated circuit. This can be done with a microcontroller that will control the power path selection. In order to move forward with our project, we need to acquire the guidance and technical support from Texas Instruments so that we can begin programming the charge parameters into the IC. The added components of our system will increase our cost by approximately $22 due to the new IC, microcontroller unit, and lithium-ion battery. Previously, the average cost for replacing a lead-acid battery was around $20 a year, summing to $120 over a 5-year period. Lithium-ion batteries have a life cycle of around 5 years. In turn, replacement during this period is unlikely, making the total 5-year cost equal to the upfront cost of $60. In the long run, this will decrease our replacement frequency, therefore reducing costs by half in a 5-year period.
For future work, we hope to complete our software development and the testing of our microcontroller unit, the MSP430. We also hope to design a functioning PCB and mechanical enclosure for deployment in Haiti. Since we'll be using a lithium-ion battery, we will see a great decrease in our mechanical enclosure size. We also hope to complete an exhaustive test of our system for deployment. Last but not least, We plan to incorporate a pay-as-you-go functionality via low-cost communication platforms enabled by Bluetooth and 3G to reduce upfront costs. We believe that by using this, we will greatly help our entrepreneurs and customers in Haiti. Thank you.